Hello, and welcome to Physics Review Videos. This is Unit 10, Reflection and Refraction. Today's topic, refraction. Refraction. What we're talking about with refraction is when light passes from one substance into another, it can bend. If you've ever stood next to a fish tank compared to looking at it from head-on, you may have noticed a discrepancy in how the fish look. Or if you've ever been in a swimming pool and dropped something down the pool, when you go to grab it, it's not exactly in the location that you see it at. The reason for that is refraction. Now, when we're talking about refraction, what we really have to look at is the factors such as the speed of light. Light in a vacuum is traveling at 3 times 10 to the 8 meters per second. But that's while it's in a vacuum. When light transitions from a vacuum into another medium, the other medium might be able to slow it down. So, when you're looking at, say, water and air, like dropping something in a pool, the light is coming from the water and then into the air. It's changing mediums, it's changing speeds, and when it does so, it bends. Let's look at an analogy to kind of visualize this situation. Let's say here, you have a nice little toy. Let's say you have one of those nice little big wheel toys or four-wheel cars, and you're driving from your driveway into the grass. Now, in the driveway, the car can go a lot faster, and the grass, it slows down. And if you drive head-on from the driveway into the grass, you're going to keep going in a straight line, but you're going to slow down once you hit that grass. Something different happens, however, if you drive into the grass at an angle. When you're driving in your driveway, it's still going at normal initial fast speed. But when you hit the grass, one tire is going to be in the grass, another tire is not. That means one tire is going to basically slower while the other one's going faster. That's going to cause the whole vehicle to bend and turn. Light is doing something very analogous when it changes substances where it can go fast to slow or slow to fast. Mathematically, then we can look at something called the index of refraction. You can kind of think about this as a ratio telling you how much light's going to be slowed down. Now, the index of refraction itself is represented by n. And n is a variable that can be calculated. It is this formula down here. And it deals with two variables. How fast light is going in any given medium. We're going to call that v. So this might be how fast light goes in water, it might be how fast light goes in diamond. But when light's traveling through a different medium, it has its own unique speed. And we're going to compare that to the speed of light in a vacuum, which is, again, that very important number, 3.0 times 10 to the 8 meters per second. Now, it turns out, based off this little formula here, n is equal to c over v. The more a medium slows down light, the larger the n value. So, an object with an index of refraction of 2.5 is going to slow down light more than an object with an index of refraction of 1.5. This also allows me to work with another particular formula, Snell's law. Snell's law, represented down here, is n1 sine theta 1 equals n2 sine theta 2. n1 is the index of refraction in your first substance or your first medium, whatever the light is traveling through before it transitions. Angle 1, or theta 1, is the angle of light when it strikes the surface of the barrier between those two mediums. That angle is going to be measured from a normal line. N2 and theta 2, then, are your index and your angle in the second medium, the one that light is transitioning into. So, for example, if light is coming from water to air, N1 and theta 1 will be in the water, N2 and theta 2 will be in the air. If light, however, is going from air to water, they would then be on the other side. So let's look at an example here to apply Snell's law. In this case, I have a laser beam firing light into the water. So, since I'm coming from this first substance in the air, I'm going to make this N1. So N1 is going to be air. They happen to give me my index of refraction here. So my N1 value is going to be 1.00. I then transition into the water. So my N2 value is going to be the index of refraction for water. In this particular particular situation is given to me at 1.33. As for the angles, I have a protractor. We have to measure our angle always from the normal line. Normal line is already shown in this image, so it's that dotted line that is a right angle to the surface. So I'm measuring my angle right here, and since that's on the side that the light is coming from, that's going to be my theta 1, or angle 1. Here there's a big question mark then for what my theta 2 is, so that's what I would be solving for in this particular problem. So if I write out my variables, n1 is 1.00, theta 1 is 50 degrees, n2 is 1.33, and theta 2 is what I'm looking for. If I were to write them in, I would have here 1.00 times the sine of 50. And keep in mind where I'm putting in my parentheses. That's going to be equal to n2, so 1.33 times the sine of my unknown angle. And from there, I would go through my solution. Now, if we quickly come back here, one thing I would like to point out is here I'm solving for an angle. The first thing I'll have to do is get rid of that 1.33. So you can do that by dividing both sides by 1.3. I'm going to rewrite this down here on the bottom. So I have 1.00 times the sine of 50. I need to get rid of 1.33, so I'm going to divide both sides by 1.33. On the right side, it would have canceled out, so that's going to leave me now the sine of my angle. When I have to get rid of my sine, you can't hit divide sign in your calculator. I have to do a different process. To get to the cancel over here, I have to use inverse sine. And as always, that has to be applied to both sides. So this is how it would look if I were to enter it in as one step. By all means, you can easily do this as individual steps and solve part by part, but this is how it would solve for that unknown angle. Now, in terms of visuals, let's look over here on the top left. I have this light ray A coming into a surface, and it comes out in a different location. So what must be happening is the light must be bending in between those two locations. And if light is bending, again, we're dealing with two different indices of refraction, and so light will be bent. On the bottom, we have here measured out with angles, showing you the pathway of the light as it transitions from material to material. Notice all these here have normal lines for the proper measurement. Now, what's neat is this can be applied when you curve the surface into things called lenses. So, for example, you have a converging lens right here, where all these parallel light rays converge at a focal point, and then you could also have a diverging lens on the bottom. And this is going to allow for some neat things in terms of different image formations, and has a lot of practical applications. But this is working off the same principle of bending light by changing your medium, changing light speed, and causing it to bend.